Hello students, welcome back to the JEE Last Mile Preparation Series 19. Today we will take up questions 37 and 38. But before I do that, by now you already know that I'm Sujata from CBSE NEET jeechemistry.in and we are bringing you 2 questions every day until April 4th to help students get that extra edge for the JEE chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. We continue with inorganic chemistry and today we will take up D and F block elements. So one question each has been chosen from D and F block elements. Question number 37. Let's first focus on D block, a question from D block elements. All right. Which one of the following options is incorrect? 4 options have been listed here. And these 4 options involve the 4 elements, namely titanium, vanadium, chromium, and manganese. So before we start discussing and analyzing the 4 given options, let's write down the configurations of these 4 elements. The first element being titanium, atomic number is 22, configuration argon 4s2,3d2. Then we have vanadium 23, argon 4s2,3d3. Chromium 24, a special configuration 4s1,3d5, right? And then we have manganese 25, configuration being argon 4s2,3d5. So first let's be sure about the configurations. Once we are ready with electronic configurations, we can analyze each of the 4 options and then get on to the correct option, the correct answer to this question, which one of these options is incorrect. Okay, let's move on to option A. Increasing number of oxidation states. And the order is titanium has got the least number of oxidation states, followed by vanadium, followed by chromium. Manganese has got the highest number of oxidation states. So let's see whether option A is correct or incorrect. For that, let's look into the electronic configuration. Now, the common oxidation state of these D block elements would be +2. So first, the 2 electrons from the 4s subshell is being lost. So 4s orbital is being lost. So 2 electrons from the 4s orbitals are lost. Okay, I'll deal with chromium soon. Now, once 2 electrons from 4s are lost, so you have the +2 oxidation state, then +3 and +4 are removed from, the remaining 2 oxidation states come from 3D. So we have +2, +3 and +4. Theoretically, +1 may be possible, but +1 is not a stable oxidation state. Same thing holds good for vanadium. The total number of oxidation states would be 2 + 3, 5. Right? So here we have +2, +3, +4. Here we have not 5, but we're excluding +1 oxidation state. We start from +2, +3, and +4 and +5. So +2 to 2 + 3, 5. Now let's look at manganese. Manganese has got oxidation states starting from +2 to 2 + 5, 7. +2, +3, +4, +5, +6, +7. And amongst these oxidation states, some of them may be more stable than the other. But these many oxidation states are practically possible for manganese. Now let's move on to chromium. So chromium, we expect a +1 oxidation state. But this is also an important discussion. Chromium +1 is not very stable. Now, why is chromium +1 not very stable? Now, these oxidation states are discussed, or the transition metals lose electrons in the context of forming complex ions, right? So they lose one or more electrons and attract the ligands. Okay, so when the ligands approach the chromium 1+ ion, the d orbital split into these two different energy levels. We call this as the T2G and we call this as the NEG. Okay, and I've just shown the octahedral splitting of d orbitals. Okay, now what happens is when one electron is lost from chromium, we are left with 5 electrons. According to Hund's rule, the T2G orbitals are first occupied by 1 electron each, and then comes the EG orbitals. Okay, now since T2G is half filled, these 2 electrons are easily lost. In order to attain the stable half-filled T2G orbital, okay, so which means we expect a T2G3 configuration. T2G3 configuration, we want 3 electrons in the T2G orbital to attain a stable half-filled state. Since this is more stable, so plus 3, so after 1 electron is lost, if 2 more electrons are lost, we arrive at this stable half-filled T2G state, and therefore plus 3 oxidation state is more stable than the plus 1 oxidation state in chromium. So in chromium, the plus 1 oxidation state is not isolated, plus 2 to some extent, plus 3, plus 4, plus 5, plus 6, and plus 3 and plus 6 are the most stable oxidation states of chromium. Okay, so these are the various oxidation states. So what you notice is as the number of unpaired electrons increase, the number of variable oxidation states increase up till manganese. But beyond manganese, from iron to zinc, you would have learned that the number of variable oxidation states decrease, mainly because of the decrease in the number of unpaired electrons and also because of the increased nuclear charges or the atomic numbers. So attraction becomes more dominant, okay, and the loss of electrons become difficult. Anyway, so here manganese will have the most number of oxidation states, and therefore the order as depicted or as presented in option A is correct. So this is a correct statement. This statement is a correct one. Now let's move on to increasing melting points. Now this is something that you would have learned theoretically, that across any transition metal period, across any deep lock period, the element with the highest melting point, for example, for the 4th period, now this is in the period 4, chromium will have the highest melting point. So all elements below chromium in that particular group will have the highest melting point in that particular period. So this is not the correct order. Okay, so this is the correct answer here. This is the incorrect option. But let's understand why chromium has the highest melting point and not manganese. Okay, for that we depend on, again, the electronic configurations. You focus on titanium. By the way, melting point depends upon the strength of metallic bond. All these are metals. Stronger the metallic bond, higher the melting point. Metallic bond strength depends upon the electrostatic force of attraction between the metal ion and the delocalized valence electrons. Okay, so greater the number of delocalized valence electrons, stronger the attraction, stronger the metallic bond, higher the melting point. So as you move from titanium to vanadium, you notice that the atomic number increases, okay, the nuclear charge increases, and the number of unpaired electrons also increase. Okay, so 4s2 is a paired electron, D2. So here there are 2 unpaired electrons. Here there are 3 unpaired electrons. So more number of unpaired electrons in vanadium, and hence stronger metallic bond and higher melting point. Now moving on to manganese. Okay, now let's move on to chromium first. Now in the case of chromium, you have 6 unpaired electrons, and all these 6 unpaired electrons are delocalized despite the stability of the half-filled d orbitals. So now let's compare the status of the stability of 3d5 in chromium and manganese. That is where the difference lies, because of which chromium has a higher melting point than manganese. Between chromium and manganese, both have a 3d5 configuration. even though chromium has got more number of unpaired electrons, we expect more number of delocalization in chromium. Okay, and that is definitely, that is what is happening. There's greater mobility of the unpaired electrons in chromium. So the thing is, manganese also has got 3d5, 5 unpaired electrons in 3d. So if you consider the 5 unpaired electrons in 3d to be less mobile, then the 5 electrons in 3d of chromium should also be less mobile. But the mobility or the delocalization of the 5 electrons in 3d is greater than that in manganese. The difference lies in the atomic number. Manganese has a higher nuclear charge, so stronger attraction to these 5 unpaired electrons. 3d5 is stable, and also these 5 electrons are strongly bonded or attracted to the nucleus of the manganese ion. As a result of which, these 5 electrons in 3d of manganese, these 5 electrons of 3d in manganese are not as mobile or as delocalized as the 5 electrons in 3d of chromium. Lesser the delocalization, weaker the metallic bond strength, right? And therefore lower the melting point. Hence, chromium will have a higher melting point than manganese. Okay, so that is why this statement is incorrect. Option B is incorrect. Chromium should have the highest melting point. Now let's move on to option C. So we know that option C and D are correct statements. Let's analyze those and therefore make you recollect the important periodic properties and some important chemical properties of the D block elements. Magnetic moments. You know that magnetic moments depend upon the number of unpaired electrons. Correct? Let's go back to the configuration. Before that, let's recollect the formula that you have learned of magnetic moment, that is equal to square root of n into n plus 2, and the unit is Bohr magneton, where n stands for the number of unpaired electrons. The number of unpaired electrons. Okay, now we have the ions here in the +3 state, right? So let's write down the configurations of the ions. Ti3 plus would be argon configuration, right? Argon configuration, here is the configuration. These 2 electrons are lost, and from 3d, one electron is lost. So you are left with 3d1. Vanadium 3 plus therefore would be argon 3d2. 5, right? So sorry, 3d3. Let's go back to the configuration. After 1 electron is lost, 2 electrons are lost from 3d5, so that makes it 3d3. What about manganese? From manganese, if 2 electrons are lost from 4s, 1 electron is lost from 3d. So for manganese, we have the configuration for the manganese 3 plus ion as argon 3d4. So most number of unpaired electrons are found in the manganese 3 plus ion. Therefore, the magnetic moment of manganese 3 plus ion will be the greatest. And from titanium 3 plus to vanadium 3 plus to chromium 3 plus, you will notice that there is an increase in the number of unpaired electrons, and the magnetic moment therefore will be in the same order as depicted in option C. So option C is also a correct statement. Now let's move on to the second ionization enthalpy. It's very evident again from the configurations of these metals from titanium to manganese that in chromium, if the first electron is lost, removing an electron from a 3D subshell becomes very difficult because it is a half-filled stable subshell. So this is the IE1 and IE2 becomes very high. So this kind of a situation is not found in any of the other transition metals. So highest second ionization enthalpy would be for chromium. The least would be for titanium. And therefore, option D is the correct, also a correct statement. Okay, so the correct answer to this question, that option which is incorrect would be option B. So I hope the discussion was clear, and I hope this particular question made you recollect some very important periodic properties and chemical properties of the transition metals or the D block elements. Now let's do a question from F block elements. Okay. Here we are dealing with a very important concept that you have come across in F block elements, namely the ionic radii. So which effect comes to your mind? Which property comes to your mind? The lanthanide or the actinide contraction, right? So you notice a decrease in radii due to certain factors. Okay, let's see what those factors are. But before we discuss those factors, let's identify in which of the periods all these elements lie. Now, yttrium and lanthanum are D block elements, are they transition metals? Okay. Now, yttrium belongs to period, comes just below scandium. Scandium belongs to period 4. So, yttrium belongs to period 5. Lanthanum belongs to period 6. Okay, now these two are D block elements. Okay, the last electron goes to the, here for 5 it goes to the 4D orbital, and here it goes to the 5D orbital. The last electron goes to the 5D orbital in lanthanum and 4D orbital in yttrium. Now europium and lutetium, okay, europium and lutetium are in the same period as the, are in the same period. They are also in period 6. They are also in period 6, but these two are F block elements. So if europium and lutetium are in F block and they're in period 6, which are the orbitals which are getting filled? The last orbital getting filled would be the 4f electrons. 4f orbitals are getting filled in both europium and lutetium. Okay, now let's look at the configuration. Look at the states, oxidation states. All of them are +3. So +3 implies that all of them bear the configuration of the nearest noble gas. Okay, but that doesn't come into the picture here because the main focus lies on the way the radii change and the way they are positioned in the periodic table. Now let's start from yttrium. Yttrium, all these elements yttrium and lanthanum, by the way, they belong to group 3. Not just yttrium and lanthanum, including europium and lutetium. All these elements belong to group 3. Okay, that is why only the different periods were mentioned here. All of them belong to group 3. You know that F block elements belong to just one group, and that is group 3. Yttrium and lanthanum are D block, are transition metals which belong to group 3. Okay, now let's start with yttrium. So you know that down group 3, down any group, as the atomic number increases, as the group number increases, the number of shells increase, the screening effect also increases, right? Now the shielding effect is seen by is due to electrons present in 4D and 5D. So 3+ involve the removal of electrons from, say for yttrium, it involves removal of electrons from the fifth shell. Fifth is the outermost shell, right? From the fifth shell. And for lanthanum, it involves removal of electron from the sixth shell as well as the 5D. So 5 and 4D, okay? So now, let's focus. Therefore, we have to only focus on the electrons present in the inner 4D and 5D orbitals or subshells. Now, the D subshells provide significant screening effect, but the screening effect of the 5D subshells in lanthanum will be more significant because they're further away from the nucleus and less strongly attracted by the nucleus. As a result of which, the size of the lanthanum ion will be much more than the size of the yttrium ion. So yttrium ion will be smaller than the lanthanum ion. Okay, the radii of lanthanum ion is larger. Now, lanthanum, europium, and lutetium, they all belong to the same period. In europium and lutetium, the electrons are present, the screening electrons are present in the 4f subshells, right? You know that the F subshells have a complex shape. And because of the complexity in the shape of F or subshells or F orbitals, the screening effect is not perfect. Because screening effect is not perfect, the ionic rate, the attraction by the nucleus is significant. Okay, so as of now, yttrium 3 plus is smaller than lanthanum 3 plus. Now we are focusing on europium 3 plus, lutetium 3 plus, right? And let's also include lanthanum 3 plus. So now europium and lutetium are present in the same period, all three of them. Lanthanum, europium, and lutetium, they're all present in period 6. And you know that across a period, the size decreases. But the decrease is not significant. The decrease is not significant mainly because of the imperfect shielding effect of the 4f electrons in europium and lutetium. Okay, so lanthanum is definitely greater than europium. Europium is definitely greater than lutetium, but because the size, the decrease in size is not very significant, okay, so because of the fact that across a period the electrons are added to the same subshell, but what happens is the screening effect is not very perfect. What is noticed is the size of yttrium and lutetium are very close. So definitely lutetium ion will be the smallest. Lutetium ion is found to be smaller than yttrium ion. Europium ion is found to be larger than yttrium ion. You might wonder how to identify that. That you can eliminate, that you can identify, or you can identify the correct option from or by some by elimination technique. So by now, from this discussion, you know that the lanthanum ion is the largest. So you can rule out options B and T, right? You also know that the lutetium ion is the smallest. So now we've got the correct answer. Lutetium ion is right here. So in this option, you notice that lutetium ion is smaller than yttrium ion. Yttrium ion is smaller than europium ion. In other words, europium ion is larger than yttrium ion. Okay, and then finally we have the lanthanum ion. So the most important discussion here is about the lanthanide contraction and also the imperfect shielding of the F electrons. All right. So these were two questions from D and F block elements. If you found these questions useful and helpful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.